Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at the homework for lesson 3.1.4. Our M&Ms describe a parabola, which you may recall from our lesson earlier in the year called Algebra Walk, where most of the graphs that we worked with were straight lines, but there was one that was more of a U-shape. That U-shape is called a parabola, and this does happen in real life situations. If you think about it, if you're playing baseball, right, and you hit a pitch and it flies out in the outfield, at some point it reaches its highest point before it starts coming down. And hopefully it goes over the wall before an outfielder can catch it. Same thing when you shoot a rocket up into the air, eventually it gets to its highest point, which is called the vertex. And then it starts to come down, and there is this U-shaped pattern. If there is no force being exerted on this object that's flying through the air, the distance that it travels to get to its highest point, it'll continue traveling on the other side on the way back down. And so in physics, science, you could use this mathematics, and there are formulas and equations that go along with these parabola shapes that can be used to predict how high something will go. And if if you're standing on the top of a cliff and you throw things off, you can figure out the speed at which it'll fall down and how long it'll take before it hits the ground. You can use mathematics to figure out these different things. So the parabola has a U-shape. It's not a V-shape. The V-shape is associated with a different type of a graph. I believe it's the absolute value graphs would have V-shapes, but it's very important when you create these parabolas on your graph that you do give it a gradual curving eventually. And we'll work more on these when we get into compound interest. I believe in chapter 8 is when we're going to get into some of our exponential functions. All right, so let's take a look at what we got for today. Complete the table like the one provided in problem number 34 for the rule y equals x plus 2. Okay, so it's a two-variable equation where the independent variable, if you add 2 to it, that gives you the dependent variable, or your input and your output. So every one of these input numbers, after adding 2, gives you your output number, and then we can take this information and plot it onto the graph and make sure you scale the axes properly. In this case, there's no need to count anything other than 1 on both your x and your y axis. You don't necessarily have to label every single one of those little tick marks. In fact, I didn't even bother putting the tick marks in, but you could have. There would be 1, there's 2, there's 3, there's 4, and so on and so forth. But you don't really need the tick marks if you've got your graph paper to show you where the next line starts. So sure enough, that is a linear equation. So after connecting the dots, you get a straight line. Now, did we need to? I guess it did say to connect the points. In this case, we connect and make it a continuous graph because x could literally be anything. You could have chosen x to be 1.37, in which case y would be 3.37. Where would 1.37 be? Somewhere around there, and then y would end up being 3.37. All right, for the following equations, draw the picture. I did not bother drawing the picture, and I'm okay if you don't draw the picture, to be honest with you. I'm ready to leave the algebra tiles and focus on the mathematics here. So if we take negative 2 plus x equals negative x plus 2, the legal moves, I would suggest collecting the x's on the left side because you got more x's on this side than that side, and that's just kind of me saying this is a positive, that's a negative, and since positives, we consider them greater than negatives, I would rather add x to the right side and zero this out so that we have 2 x's on the left side, then take away this x and have to deal with negative x minus x is a negative 2 x's. I would rather keep my coefficient for my x term a positive number, so I'm looking to see which coefficient of our x's is the greater number, and 1x is greater than negative 1, so let's collect them on the side of the 1x, the positive x, which means we'll want to collect our number on the right side. So we'll add 2 to each side, and that gives us 2x equals 4. And so what do you multiply times 2 to give you 4? X has to be equal to 2. Now, I'm going to show you this here let me just cover that up for a second, because I like doing this in as few steps as possible, and I think you'll appreciate that as well. What do I need to do here? I'm going to block this guy out. Let me take this and do that. Let me get rid of all that. All right. So this is what I would do. I would say, since I'm going to collect my x's on this side, I'll add an x to each side, which is going to cancel them out, right? And in the exact same step, I'll take care of adding the 2 to each side to cancel them out. So we've got our equal sign here. You got our 2 x's on this side, and you got your 2 x's on this side, and you got your 4 on this side. And there it just took up a little bit less space, right? So if we did that here, I would take away this x, but I would also take away that 2, and then these cancel, leaving you with 2x is equal to 5. You skipped that middle step. I am absolutely on board with you taking this and using this process to make your work as short as possible. I can follow your logic of what you're doing here when you combine those 2 steps into one big step, okay? Or you can separate it out and take 1, 2, 3 steps to get to your answer. All right, evaluating means we're going to take our value for x and plug it in here and use the order of operations. So 4 times 8 is 32, and 32 plus 5 is 37. Here you've got 2 variables. I guess, no, we only have the one. We're going to plug in where c is equal to negative 0.5. So 5 times 1/2 is 2.5, but then that's a negative 2.5. So it's 3 minus negative 2.5 means you're going to add, okay? So take a look at these numbers. If you don't know how to get those answers, let me know and I will work those out for you. Otherwise, I'm going to move on because I want to make this video as short as possible so you can get on to your work for the day. Peggy Sue decided to enter her famous 5-alarm chili at her local chili cooking contest. Normally, she needs 5 tomatoes to make enough chili for a family of 7. So that is a rate, right? Whether you put the people on the top or the tomatoes on the top doesn't really make any difference, to be honest with you, when you're using proportional reasoning. But it would make a difference if you were using a unit rate, like the amount of tomatoes per people or the number of people per tomato for the chili. If you wanted to use the unit rate, you'd have to be aware of the order in which you're writing these, which one goes on the top and which goes on the bottom. But since in this case we're just going to solve for x, it technically doesn't matter. Just say 5 tomatoes feed 7 people. So how many tomatoes would feed 100 people? So this is an example of a situation where what are you going to multiply times 7 to give you 100? Those are horrible numbers. So I would recommend doing the cross multiplication. That works easiest when you've got unfriendly numbers and you just use your calculator. 7 times x is 7x, 5 times 100 is 500, and now we will take 500 and divide it by 7 to figure out what x is. In this case, it gives you a decimal number. So technically this would round down to 71, but then 71 wouldn't take care of 100 people. So you'd want a 72nd tomato to guarantee that you'd have enough chili for 100 people. The second question said, when she gets to the contest, she realizes she only packed 58 tomatoes. So how many can she expect to feed? So same ratio, but now the number of tomatoes would be 58, which has to go in the same row as the 5 tomatoes. So now we do the same thing, cross multiply and then divide. And so this would be able to accommodate about 81 to 82 people, somewhere in there. At the annual dog show, Chantel noticed that there were 3 more Scotties than Schnauzers. All right, Scotties and Schnauzers. She also noticed that the number of wire-haired terriers was 5 less than the number of Schnauzers. Okay, so let me actually start over. And it looks like they're both being compared to Schnauzers. So I'm going to make Schnauzers my X. So what's the comparison with Scotties? 3 more Scotties than Schnauzers. So whatever the number of Schnauzers is, add 3 to that, and that will be the number of Scotties. And the wire-haired terriers was 5 less than twice. So 5 less than, you have to use the order of operations. So double the amount of Schnauzers and take away 5. So this is 5 less than 2 times that. So once we all that in order, we know our number of Schnauzers is an unknown quantity that we're trying to figure out. That's our X. And then compared to the number of schnauzers, you got x plus 3 for the Scotties and 2x minus 5 for the wire-haired. So now let's solve this equation by first simplifying the expression on the left. X plus 2x is 4x's, and 3 plus a negative 5 is negative 2. So we would add 2 to each side to get 4x equals 80, and then we divide each side by 4, and you see that the number of schnauzers must be 20. If you wanted to know the number of Scotties, it would be 23, and the number of wired hairs would have to be 40 minus 5 is 35. You want to go through this process because you need to figure out if this is the right answer. And the only way we'll know there were 20 schnauzers is if 23 plus 20 plus 35 adds up to 78. So let's check that. You get an 8 here. 4, 5, 6, 7. Yes, it does. So we can declare how many schnauzers were there? There were 20 schnauzers. And that's where we end today. Is it less than, oh, we're just almost to 10, almost to 11. All right, so let's head over to the home, to today's lesson. Here, bye.
Hey, feeling good.